All right. So here are a few kinematics, rotational kinematics MCQ questions for you to learn. Um, the first one is this one. It says an object moves from A to B along a circular path of radius r, and it wants us to find the size of the angle in degrees. So here's a diagram for you. Here's A, and then it's gonna go clockwise to B, and the arc length traced out here is L, which is also the radius of the circle. All right. So for this one, it's pretty straightforward. To find the arc length, to find the angle, you have to use the arc length function because theta is given and arc length is given. So you might as well just move on with this particular problem using arc length. Is equal to r theta. S here is arc length, r is the radius of the circle, and then theta here is the angle that it traced out in radians. So keep that in mind. So here in the problem, it says the arc length happens to be L. So if you look at the diagram from A to B, the diagram labeled that arc length of L, which also is equal to the radius of the circle. So I'm going to replace S with L, which is a true statement. And then the diagram uses capital R, so I'm just going to replace lowercase r here with capital R just for the sake of consistency here. And then theta here, once again, just gets carried down. But the problem says that the arc length, which happens to be L, which is also the radius of the circle in this particular problem. And that's it. So I'm just going to replace S generically, arc length with L. L is also R, so really a bunch of true statement here. All right, so as you can see here, there's an R on the left, there's an R on the right. At this point, if you want, you can cancel R and R. That leaves you just 1. But I'll just go ahead and divide both sides by R just to help you visualize algebra stuff here. R divided by R is just 1, so therefore theta here is just 1 rad. Okay. However, the question wants us to find this in particular, or at this angle in degrees. So let's go ahead and convert 1 rad to degrees, and we'll be done. If you know unit circle, use it. So here, if you go from 0 degrees to 180 degrees, that's in degrees. But however you want to express 180 degrees in rad, that would just be pi. So we would say that 180 degrees is pi rad, or vice versa. So I'm just going to go ahead and convert that 1 rad that I just found. So here's 1 rad. 1 rad is equal to 100 degrees over pi rad. So make sure you put the numbers where it needs to go. Rad will cancel out, and that just leaves you with units of degrees. So if you do 1 times 180, which is 180, and then 180 divided by pi, which is 3.14, will give you roughly about 57.3 degrees, which matches answer choice B. Okay. All right, let's move on to the next one. This one wants us to find the angular displacement of a car wheel that has a radius of 9 meters and has to move through an angular displacement of 3 rad. Once again, you notice here angular displacement is given in terms of radians, not degrees. So it wants us to find the linear distance or linear displacement here. So I just gave you a visual here. Here's a bicycle wheel that it's gonna rotate, or a car wheel, whatever you want to use. So the linear displacement is just the linear distance, but if you think distance, you have to think of arc length. Okay. So here, linear distance is what we're interested in. So I'm gonna use the same function that I did in the previous slide. Why? Because I need to find arc length. So here, instead of S, I'm just going to call X, because this animation that I used traced out the horizontal axis here, or the linear distance. Here, I'm just going to X is equal to the linear distance, and that also equals to R theta. And then I need to find X. R is giving us 9 meters. Theta is giving us 3 rads already, so I don't have to convert. So make sure you understand which units you need to be in as you practice this problem, okay? Angular displacement is rads. So it's already in rad. If it's not, let's say if the problem gives you degrees, convert degrees to rad, and then move on. All right. And that 9 times 3 is 27. So the linear distance that this particular car wheel traces out after 3 rad is 27 meters. All right. That's it for this one. It's pretty straightforward. This one it's a little bit trickier, but this one's pretty factual though. So here you have this as rotating by center of mass. The radius of point A is 0.06, and then the radius of and then point B is 0.12. So right away, I know this one's pretty easy. This is 0.06 and then 0.12, which is a 1 to 2 ratio. So essentially 0.06 is midway, and then 0.12 is twice as much. So I'm just gonna put 2 dots on my circle here from the midpoint and then to the outside. It doesn't really matter. You can put 0.6 where you want. As long as 0.12 is double 0.06, you'll be fine. All right. So it says here which of the quantity is the same. So again, we're looking for a statement that is the same. if the disk accelerates from rest. All right, so let's go ahead and do it. I'm just going to take it one answer choice at a time. Choice A says the angular displacement is the same. Well, the angular displacement is the same because the disk rotates as a single unit. Because this rotates as a single unit, every point on the disk will trace out the same angular displacement or the same angle. So here I have a couple of arrows for you. For example, once this system starts to rotate, the inner dot here at R/2 is going to rotate a certain angle. However, because it's on the same line, the point on the outer edge of the circle will also trace out the same angle. Not arc length, just the same angle, okay? So both these dots will have the same angular displacement because they trace out the same angle. So this is a fact. So I put here change in theta is the same because they both trace out the same number of degrees, which can be converted to rads. All right. The next thing that you need to know is that because the disk move as a whole, as a one unit, the angular speed or the angular velocity of all these points must be the same because, well, omega is theta over time. If theta is the same from the first bullet, well, it's a single unit, so every single point has to have the same time. So theta over t must be the same because the same theta, same time gives you the same angular velocity. All right, and then last but not least here, well, if angular velocity is the same, angular acceleration must also be the same for every single point on this particular disk because angular acceleration is defined as angular or the change in angular velocity over change in time. Well, if the angular velocity, which is omega, is the same, times the same, so therefore angular acceleration must also be the same. Okay, so let's go ahead and crack out A, B, C, D, and E here. So part A, I'm just going to write the angular displacement function, which is omega I t plus 1/2 at squared. Omega I is 0. So really, the fine change in angular position here, or the angular displacement, I need 1/2 alpha t squared. Well, same time, same alpha, therefore angular displacement must be the same. It's that easy. All right, let's go ahead and do B. Even though I know what the answer is, let's go and teach you how to do B. B says the angular displacement is the same. Oh, excuse me, the linear displacement is the same. Well, linear displacement is just the arc length, and arc length once again can be written as S equals R theta, or X here is equal to R theta. Well, R is different because the inner point has a different R because it's R/2. The outer points are, however, right, theta is the same. So theta is the same, so the only thing you have to focus is on R. Well, R is different. If R is different, then X has to be different. They cannot be the same. So therefore, choice B is off. Now, if you can just visualize a couple of circumferences, I just kind of did a couple of dash line here for you. The point on the inside of this particular disk at R/2 is going to trace out a smaller circumference, while the point on the outside traces out a bigger circumference. Just using common sense, if you're on the outside, you have to cover more distance or a bigger circumference in the same amount of time. To cover more distance in the same amount of time, you have to be moving faster. In this case, you can also use this as an elimination of choice B. Just by deduction, the point on the outside covers a larger circumference. Therefore, linear displacement cannot be the same, right? The point on the inside covers less distance. The point on the outside covers more distance. So that cannot be an answer choice. Let's go to C. Choice C says the tangential acceleration. Well, the tangential acceleration is dependent of R and angular acceleration. Once again, we established earlier that the angular acceleration is the same, so alpha is the same based on this particular statement on the bottom, right? Same omega, same time, therefore acceleration must be the same. However, this function depends on R. Well, both these points that I have in red here has different R's, so therefore we can say that A tan is different. The object on the inside has a slower tangential acceleration. The point on the outside, because R is bigger, will have a larger tangential acceleration. All right, but I need stuff that's the same. A10 is not the same. One's big, one's small, so therefore I can cross out C. Choice D. Choice D says the tangent velocity. Well, if you kept up my reasoning earlier, if you're on the outside, you got to run faster, right? You got to cover more distance in the same amount of time. So tangential velocity or speed cannot be the same. That's crazy. Or you can just justify using physics function here. V is equal to R omega. If omega is the same and R is different, well, if bigger R, bigger V, smaller R, smaller V. So therefore the point on the outside has a bigger R. Therefore the point on the outside has to have a greater tangential velocity or tangential speed. Alright, so we're looking for the stuff that's the same, so let's cross out D. Alright, V cannot be the same. And last but not least on this one, centripetal acceleration. Well, the centripetal acceleration is just R omega squared. Once again, omega is the same, therefore it depends on R. If R is different, A, C cannot be the same, so I want to cross that out. Here's the other one. Here is the graph. You're given omega versus t, and it wants to find how many rotations it covers during this particular 10-second in the graph. So let's go ahead and do it. I think the easiest way to do this one is just to find the area underneath the graph. You're given a velocity time graph. The area underneath the velocity time graph is your displacement. So here in this case, even though it asks for rotations, I can find the angular displacement and just convert it to rotations. Okay, so I made a note for you here. The area beneath the velocity versus time graph is your displacement, and this is positive displacement, so therefore is above the t-axis. So I'm just going to go ahead and just find this particular area using math function. A is equal to 1/2 times base times height. Here my base is 10 because the graph gives us 10 seconds, and it actually wants us to find the number of rotations over 10 seconds, right? So I'm just going to use the whole entire graph. Alright, so base is 10, height is 8. 1/2 times 10 is 5, 5 times 8 is 40, and then the unit S will cancel out. That leaves us with 40 rads. But once again, the question didn't ask you for how many radians, it asked for how many rotations. So you need to convert 40 rads to number of revs, because revs and rotation are the same. Alright, so here the area is 40 rad, so therefore angular displacement, which is the area underneath the graph, is also 40 rad because they represent the same quantity. So I'm just going to go ahead and bust this out again. Well, to convert 40 rads to the number of revolutions, you can just use a couple of conversion factor here. You can use pi, which is equivalent to 180 degrees, or over here you can use 2 pi radians is equal to 360 degrees. So I'm just going to go ahead and use the 1 rev here is equal to 2 pi rad. Again, you don't have to, you can just do whatever you want. But ultimately, I like to think of it for you to do 1 complete rotation that's equivalent to 2 pi rad. So why not, right? So here you have 40 rads to start because I already found the area, which is 40 rad. I'm going to convert rad to revolutions because revolutions is the same number as rotations. For every 1 revolutions, that's equivalent to 2 pi rad. Rad cancels out. So really you have 40 times 1, which is 40. And then 40 divided by 2 pi will give you about 6.36 revolution, which is, once again, is the same as saying rotations. So the only answer choice that makes any sense is choice E, because it says more than 6 rotation, and 6.36 is more than 6. But it's less than 7. So let's go ahead and just highlight E and move on. Alright. If you don't like doing area for this one, in case you don't know that the area beneath a velocity time graph is your displacement, then you can use your kinematics equation. Here, I can use the omega average functions. Omega average is just displacement over time, or you can take omega f plus omega I divided by 2. But keep in mind, you can only use these particular functions if angular acceleration is constant. Well, how do I know if I can use it? Well, just look at the graph. This is a velocity time graph. The slope here is a constant negative slope. Well, the slope of a velocity time graph is your acceleration. Well, the slope is constant. Therefore, acceleration is also constant. So I can use that. So I'm just going to go ahead and isolate for delta change in theta here, or delta theta, by multiplying both sides by t. Ultimately here, really, if you think about it, you have everything you know. Omega f is 0 because at 10 seconds it comes to a stop based on the graph. Omega I is 8 because the graph said so. And then you divide it by 2 because that's part of the function. And here the change in time here is 10 seconds because the problem wants us to go all the way to 10 seconds. So if you plug and check, omega f is 0, omega I is 8, 8 divided by 2 is 4, 4 times 10 is 40. As you can see, the angular displacement is 40 rads, but you need to convert 40 rads to revs, which is already done for you. Okay, so here is just different strategies if you want to use kinematics rather than just analyzing a graph with the area provided for you. All right. Last but not least in this one, We have a toy car that moves in a circular track of radius 10 meters, and it says the car's velocity is instantaneous, directed south. I think this is essential here. Its acceleration is directed west at 10 meters per second square, and it says when view from above, the car moves, so on and so on. So if a problem doesn't give you a diagram, I highly suggest that you draw one for you. So I underlined it, the word or the phrase here, directed south, because that's important, right? It says at some point the car is moving southward. So here geographically, south is down the page. So here I gave you a car that has a velocity pointing south, which is down the page. Therefore, over here, AC is pointing towards the center of the circular path, which happens to be left in this particular problem. So if you look at this one, the car is currently moving in a clockwise direction, right? So I can cross out like 3 answer choices. I can cross out C because this is counterclockwise. It doesn't match with the information given. When you're directed south, and then the acceleration is west, which matches this diagram, which suggests that the car is moving in a clockwise direction, not counterclockwise. So I can cross out C, D, and E. Now I'm left with A and B then, right? Because it's moving clockwise. So how do I do this? Well, generically, the centrifugal acceleration by definition is just V squared over R. However, if you know your bridge function, I call it, V equals R omega. Again, if you don't understand this, then you probably was confused in the previous slide, because I made a statement that V is equal to R omega. So here I can substitute out V. V is R omega. You make sure you use parentheses. I want to distribute the exponent, so R and omega become square each. So R square, omega square. And as you can see, there's an R square on the top and there's an R on the bottom. So I'm going to cancel one of the R's out. So essentially, generically, we can say that the centrifugal acceleration is the R omega square. Well, here I have R, which is 10 meters, which is given in the problem here. And then what is this? I don't know what omega is, because that's what the question is asking me. Essentially, it says when viewed from above, the car moves, and all these are units of rads per second, which is your angular speed. But I do know what C is, right? It says the acceleration is directed west at 10 meters per second square. So AC here is 10 meters per second square. R is given, so I'm just going to do math, or I'm just going to do algebra. I'm going to isolate for omega squared, dividing both sides by R. I'm just going to replace A with 10. R is also with 10. And then I want to square root both sides to find omega. So if you keep it right now, 10 over 10 is just 1. The square root of 1 is just 1. So let's go ahead and highlight choice A. Alright, that's all for this particular video. Stay nerdy, don't be bored.